Now, when talking about fission and fusion, I think we need to start out talking about why it actually occurs. All atoms are always trying to become more stable, which means they're trying to increase the binding energy or how much energy is stuck in the nucleus. Now, one of the ways they can do that is through radiation, but if they need to make a big move, not just a small step somewhere, they need to make a big move. Fission or fusion actually works really, really well. In fission, you're going to split large atoms. So a large atom actually splits apart, and thus you end up with a very large movement. Or if you have smaller atoms, you can combine them together. That's fusion to become more stable. Now, check out this graph over here to try to understand this idea of binding energy. Your most stable isotope lives right up here around iron. Notice that the iron isotope, iron 56, actually has the greatest binding energy per nucleon. In other words, if you took how much energy is per the number of guys inside the nucleus, it actually has the greatest there. In other words, they're the most stuck together. Now I'm going to talk about that here in a moment. But everybody's trying to become him. Now they don't all get there, obviously, but in the end, everyone's going to try to become him. And so all of these lighter guys will happily go through fusion to end up getting to him. And I say happily, I shouldn't say completely happily, but they'll go through fusion. And these guys over here, they'll go through fission to end up becoming towards iron. So in the end, everybody's trying to, if you will, we'll use the word increase right now, increase their binding energy or become more stable, more stuck together. Now, this table up or this graph up here is the common one that we use for explaining things, where we just kind of make everything positive because it's a little bit maybe easier for many people, many students to understand. I actually prefer this graph down here, where everything's actually negative, which is actually true. Binding energy, in fact, all potential energies are negative, and so what's actually happening is you are decreasing the energy whenever you go through fusion. So whenever you go through fusion down here, you're actually decreasing the energy, becoming more stuck or more. If sometimes it helps students to think of it as more buried in a hole, right? The more stuck together all the atoms are, the more buried in the hole they are together. And then fission, same thing. You're actually becoming more stuck down here towards iron. But for now, we're okay living up here, and like our binding energy is increasing. But I just don't want you to get confused whenever I start talking about how the mass actually goes down over here. The energy is decreasing in the nucleus overall. It's because it's actually negative, and that's not something that we overly need right now. But just want to give a little point to that. Now, fission is what we actually end up using a lot right now in our world. I say a lot, and it's not the primary source of energy production in our world right now. But fission is something that we can actually do. See, what you do is you take a very large isotope that is unstable. So like uranium-235 is the most common isotope that we end up actually putting through fission right now. Which, by the way, uranium-235, kind of side note, very difficult to actually obtain. Around a little over 99%, 99 points and change percent is uranium-238, an isotope that, while unstable and goes through radioactive decay, it isn't so unstable that it fissions. And so because of that, since there is so little uranium-235, whenever you dig up uranium from the ground, you mine it, it's actually very hard to obtain enough uranium-235 to actually do anything. It's one of the international things if you start thinking about nuclear power production and then eventually with some countries nuclear weapons, why it's so difficult to develop those. Anyway, uranium-235 goes through fission. What we need to do is it's unstable, but it doesn't want to fission just naturally on its own. So we give it an extra neutron. You basically shoot a neutron in at relatively low velocities so that it'll stick in here temporarily, just for a moment, forming uranium-236. Now, that guy is unstable. It doesn't live very long, and it happily splits apart. And whenever it splits apart, it splits into two somewhat random different isotopes. Releasing also some other neutrons and a whole bunch of energy. These guys go flying off with a lot of kinetic energy. You'll also get some gamma rays out as well. And so what ends up happening here, if you think about energy, the energy stored inside the nucleus here compared to the energy stored inside the nuclei of these guys, these guys are separate. The energy stored inside the nucleus actually decreases. And remember that E equals mc squared. And so energy has a quantity of mass. So if the total energy stored inside the nucleus decreases, that means that there's going to be a mass difference. That means this guy over here, these guys over here on the left, the reactants will actually have a greater mass than the products. And if we total up their masses and then subtract these guys' masses, I'll end up with a mass defect. In other words, the mass, the mass value of the energy that was released, and then I can easily calculate how much energy that was. Now with fusion, fusion is similar, except we're combining small atoms together to become more stable. Now fusion, we haven't been able to pull off. We can do fusion, it's just not energy positive right now. The amount of energy that we have to put in to make these fusion atoms, or to make these light atoms actually fuse together, is greater than the energy we get out. Now we know it works because fusion is actually what drives our universe. Fusion is the energy production source of our entire universe. You see it every day in our sun. It's what drives our sun. And so this is actually a fusion that occurs very often in our sun. Deuterium, or H2, a isotope of hydrogen. It has one proton and one neutron here, combines with, if you will, plain Jane hydrogen, which is just a proton. And in that, we get out helium-3 with a lot of energy. Some gamma rays come out, and this helium-3 goes moving off with a lot of kinetic energy also. Now the advantage of fusion, kind of an aside here, the advantage of fusion, yes, helium-3 is slightly radioactive, it would decay, but it also happily fuses again to get to helium-4, and so you have something that can quickly be fused again. So in the end, with your fusions, you don't end up with anything radioactive there because you can keep fusing things together until you get to something that isn't radioactive. Whenever you go through fission, it's kind of the opposite. The results of my fission reaction won't split again, and because of that, it's useless as fuel, and I'm left with these two very radioactive particles, sometimes with very, very long half-lives that I've got to now store this nuclear waste for some time, and then that's an issue that our world has been facing as well. Now back to fusion. Put together the two small atoms and you get out a slightly larger one, and because of that, the amount of energy that is stored in the nucleus actually goes down, making it more stable. The total energy stored in this guy here decreases compared to that guy there, and so because of that, remember there would be a mass defect if I subtract the masses of my products minus my reactants minus my product over here. I'll actually find a mass defect. That's the value of the energy actually released. Let's do a fission example problem here. Let's use uranium-235 just like we had on the last slide. And whenever it goes through fission, in this case, we're going to get out krypton-89 and barium-144. Now, fission products are somewhat random, and so you're actually going to have to be told at least two of the three things that actually comes out and what your reactants are as well. So the majority of the equation is going to actually have to be done for you one way or another. The first step whenever you have a problem is to write a balanced nuclear equation. Now, a few things about the balanced nuclear equation that I just wrote. I was told my initial, my reactants, the initial things that I had, a neutron, which has one nucleon because a neutron would go in the nucleus, but is not a proton, so bottom number 0, and uranium-235. Now, whenever it says uranium-235, it didn't actually tell you that you had 92 protons, but remember that the proton number identifies the element. So you just pull up the periodic table, find uranium, and then you know that you have 92 protons. It also told me my products here. I've got krypton-89. Once again, look up the proton number down here off the periodic table. Krypton has 36 protons every single time. And barium-144, that'll have 56. So 36 for krypton and 56 for barium. And then I know that I'm going to get out 3 neutrons. So besides knowing that off the picture, let's talk about how you would end up knowing that. In fission reactions, all of them end up releasing a few extra neutrons, which then can go on to cause chain reactions. So they move off a little too fast. You're going to need to slow them down. But if you think about this, these neutrons can go off and hit another uranium atom, and thus causing the cycle to continue, causing a chain reaction there. How do you figure out how many neutrons or what this is? It's just simply that the number of nucleons ends up needing to balance out, and the number of protons ends up needing to balance out. So if you check this out, 1 plus 235 is 236. 89 plus 144 is 233. I'm 3 short on my nucleon number. But 0 plus 92 is 92, and 36 plus 56 is 92 also. So I'm just fine on my proton number, meaning that whatever I'm going to have over here is going to have a 0 for a proton number and has to be a nucleon, has to have 3 of them in essence. So we can use a neutron, right, because it has its one nucleon. And if we use 3 of them, then this all balances out exactly how it should. If you weren't given, let's say, one of the products, something was covered up, then you would just simply subtract nucleons, reactants minus the products. And then likewise over here, if you with the number of protons, to figure out what your unknown might be, whatever ends up being your unknown. Just remember that protons, the bottom number, and the number of nucleons, the top number, do have to balance out. Now, to find the energy released, all I need to do is find the mass defect. So I need to subtract the mass of my reactants, the mass of reactants, minus the mass of my products. And that ends up getting me a mass defect of 0.186013 AMUs whenever you subtract. Now to find how much energy that is, if I want it in joules, multiply by approximately 1.5 times 10 to the negative 10th. And that gives me in the end about 2.79 times 10 to the negative 11th joules per fission reaction, which seems very, very small. But remember that whenever we do fission here, that we can pack in a lot of uranium-235 atoms. I mean, we can pack in times 10 to the 23rd number of atoms there that can actually go through this fission, and each one of them giving us almost 3 times 10 to the negative 11th joules. With that many atoms, you actually can get a lot of energy out. Let's do one more example problem, this time with fusion, although it works pretty much the same way whenever we're talking about how to calculate the energy out, as fission does here. So I'm going to fuse deuterium and hydrogen, regular hydrogen, which is a common one that ends up happening in our sun. And so whenever I first go through this, the very first thing that I need to do is write a balanced nuclear equation. Once again, notice that the nucleon numbers balance out and the proton numbers also balance out. So in a fusion reaction, if one of your things was blank that you had to fill in and figure out, you would just simply pick whatever numbers you needed to balance it out. So for example, if this was blank over here, I'd say 1 plus 2 is 3, so that number has to be a 3. And then 1 plus 1 is a 2, so that has to be a 2. And the element should have 2 protons. The proton number identifies the element. And then look on the periodic table, and I would find that it was helium. And to figure out the amount of energy released, right, I'm going to take the masses of the reactants minus the mass of the product to figure out what my mass defect is. That's the value, the mass value of the energy that was released, and then I can figure out what amount of energy that is just through a simple conversion. So I end up with my mass defect, and then whenever I'm trying to convert from my mass defect here into the amount of energy, I just simply need to multiply by the conversion that was already done using E equals mc squared for me, right? 1 AMU is going to be worth, if we're trying to get to joules, which in our class right now we are, times 1.5 times 10 to the negative 10th joules is worth 1 AMU, and I'm setting that up with the AMUs on the bottom right, so then it would cancel out. And that in the end will give me 8.85 times 10 to the negative 13th joules of energy out, which is actually an interesting observation if you think about that amount compared to the fission amount. Generally, per reaction, fission will actually give you more energy than fusion. But the fission, the things that you can fission are so much heavier that you generally can't, it's generally harder to have more of it. And so it's actually easier. Fusion, you can have more of your reactants because they are much, much lighter there. I mean, hydrogen it has a mass number, right, of 1 or 2 if we're doing deuterium, where uranium has a mass number of 235. So while per reaction fission will give you more, generally fusion will actually end up giving you more energy output in the end because your reactants are so much lighter, you can put more of them in there.